Back from afternoon tea. We're just about to get underway, so those people who are just coming through the door, can you move a little quicker and take your seats? This afternoon we have a speaker who is very well known, Jonathan Corbett, and I have a bio here which I've been very fortunate to read out earlier in the week. Jonathan Corbett is founder of LWNnet and the author of the kernel page. He is co-author of Linux Device Drivers, a member of the Linux Foundation Technical Advisory Board, and a regular contributor to the kernel. His title up there is Some Challenges for the Linux Development Community. The title that you may have read is Challenges for the Linux Plumbing Community. They are both probably quite the same, and I'm not at all surprised to discover that we have challenges. Everyone, please give Jonathan Corbett another warm welcome.
First challenge? No. One down, reboot.
There you go, you're on.
I'm on? Okay, yeah, very good. First challenge overcome already. All right, well, people who have seen me talk in the past know that I'm really good at getting out and saying that things are really going great. All right? Linux is everywhere. It's in our handsets, it's on our laptops, it's on our supercomputers. We do all supercomputers, right? And so on. The code is advancing quickly, the development process is trucking right along, our development communities are healthy, we're doing great. And I get up and I tell people about this fairly often, but after a while that gets a little bit boring. Just sort of say that, yeah, we're doing good and all that sort of thing. And in fact, there are some things that we have to be concerned about, some things that we can think about, even if the problems that we have could be described as being high-quality problems. Nonetheless, there are always things that are worthy of attention. This talk was initially written for the Linux Plumbers Conference, which is why it had plumbers in the title. And so the call to action, of course, was that we need to get out our tools and address the challenges that may be before us, or at least a few of them that I'll talk about. So the one I want to talk about first is one that people get tired actually of hearing me harping about, but I'll do it anyway, because security is an issue that I believe we do not address with sufficient seriousness in any way. If you look at some of the things that have happened over the last couple of years, look at what's been in the news. You hear about the Stuxnet worm, which was an attack on another country's industrial infrastructure, and so on. It's the compromise of RSA security and the information there. Just a few months ago, actually, I got a new RSA key from my bank saying, we thought you might like to have one of these. Please use it. Oh, no, throw that other one away. They didn't tell me why. We heard about a registrar called DigiNotar, which was compromised. These, their facilities were then used to create fraudulent SSL certificates that were used to perform man-in-the-middle attacks on people in Iran trying to get through to Gmail and other places like that. This is serious stuff. And of course, there was the compromise of kernel.org, which was discovered last August, and which disrupted our processes quite severely for quite a while. So I find all of these things to be pretty scary and pretty eye-opening. But the thing that I find the most scary of all is the fact that we certainly don't even ever hear about the bulk of the things that happen out there. Either because the compromises have not been discovered, or because they are discovered and they're silently swept under the rug and fixed up, hopefully fixed up, and so on. I mean, if you think about it, you've just got to realize that there's a whole lot going on out there that we don't know about. And this is not good. The point that I'm trying to make is that there are not only bad guys out there, but these are very strongly motivated bad guys. They're very well capable, they're very highly skilled, and they're well funded. These are people, some of whom have the resources of national governments behind them. We're not just dealing with the sorts of attacks that we used to back when we thought that all we had to do was defend against the script kiddies. and we were safe, right? It's not just script kiddies anymore. In fact, it hasn't been for quite some time, of course. There's been a lot in the way of attacks that were financially motivated and such, but really it's not about money anymore either. When you think about governments performing man-in-the-middle attacks against their own citizens, or the sorts of stuff that went on in Egypt, for example, and so on, it is not hyperbolic. It is not exaggerating anything to say that lives are at stake here. It is really true, and I think it's going to become increasingly true as people and governments fight for power in the coming years. And the simple fact of the matter is that we are on the front line. A lot of these people are running our software, and they are depending on us to help keep them secure. And we are all on the front line, by the way. I'm not just talking about the people who write something like SSH, something that we think about as being security critical. A recent jailbreak attack on the iPhone was done by way of a vulnerability in the free type library, not something that you think about as being a security critical piece of code, right? Something that can jailbreak an iPhone can compromise it and turn it against its owner, even more against its owner, shall we say. Right, there is no code that is not security critical, I don't think, at this point. It's something that we all have to be thinking about. So what I've done is I've put together some stuff that I really think that we should all be thinking about as we do our development. Starting with, is your code secure? How many of you out there work on projects that have enough review bandwidth? Have no problems with review at all? Last time I asked this question, a couple people raised their hands, and I called them liars. Right, review is in critically short supply in every project. There just isn't the people time to look at the code the way we pride ourselves in doing, quite frankly, and certainly the way we would like to do it. And when we think about reviewing code for security-related issues, it's even worse, because it takes a particular sort of demented mindset to look at code and think about how you can break it in that way. It's not an easy thing to do, and it's not something that comes naturally to a lot of us. So a lot of code is being shipped to people that has never had this kind of review applied to it at all. Testing, what sort of testing do you do? What sort of security relevant testing do you do? Do you do fuzz testing on your project, for example? I don't think a lot of people do. What about testing for security problems that have been found and fixed? I know in the kernel we've had a couple of really embarrassing incidents where we have reintroduced security problems that had been fixed, and then somebody comes through and sees something and they put it back in just the way it was there before. And that is, it's sad, and it's really not something that we would like to see happen, and it's preventable if you have testing for these sorts of things. And finally, what do you do if, or perhaps shall I say, when a vulnerability turns up in your project? How do you get the word out there to people? How do you get fixed code out there to people? Some projects are very good about this, some are not. Some distributions are very good at it, some are not. So if there's a hole in your laptop, chances are pretty good it can be fixed. I really worry about things like handsets, or about little home routers, or things like that. They will sit there and they will run for years without any attention at all, and they're sitting on the front line in terms of, in a security sense. Sometime I think we're really going to get burned because we don't have the plans for getting the fixes out there where they need to be. What about your infrastructure? Of course, the attack on kernel.org has brought this to mind for a lot of people. Who has access to the systems you're using to host your repositories, your distribution sites, and so on? Right? Kernel.org had 450 shell accounts on the master machine. That certainly led to the compromise and led to the spread of the compromise elsewhere. That is not something that you really want to have. I know that there are other hosting facilities out there for other projects that have similar levels of access to them now. And when you've got that many people who have credentials to get into a system, no matter how careful those people are, I think it's really only a matter of time till something happens. Who can change files on the systems? We had an incident, I guess, a couple of years ago now, where somebody got drunk and just committed a bunch of code sort of dissing one aspect of the project that they didn't think was doing good work. And no harm was done there, but it kind of showed what can happen if somebody with access to the code can change things. Security updates, again, on your infrastructure. Is your infrastructure secure? Have the known holes been fixed? And what is your plan in case of a breach? This is an area where a lot of us fall down. You run your system, you apply your updates, you keep an eye on it, you check your log watch output. You really try to make sure that it stays secure. But what happens if somebody gets into it? How are you going to respond to that? And we've seen a number of incidents where the response has aggravated the problem, has made the forensic and recovery work harder, and has just complicated things all around. You need to have a plan. You need to know what you will do if your infrastructure is broken into. And I don't think very many projects do that. And finally, what about processes? Who can commit code? Who can put it in the repository? And what do they know about where that code is coming from? If somebody out there set their mind to the task of deliberately inserting a vulnerability into your project, would you catch it? Would you know about it? Would you even have a clue that there's code coming in from somebody who isn't who you think they are? Very small projects, maybe they would. Otherwise, it's really hard. This is a hard problem. You gotta keep an eye on things. Who can sign releases and actually put them out there? Who can put a signature on tarball and make it look like it's truly an officially released tarball from your project? And can you detect tampering? Are you using source code repositories that can detect various types of tampering attacks? Do you have means for checking your distributed files from somewhere else offline and seeing if they've changed? That sort of thing. All this sort of stuff and a whole lot of other things that honestly I think every project out there should be thinking about if they want to be sure that they are serving their users and not setting their users up for something really unpleasant in the future. And in general, I just want to say, to finish with security, we need to be careful. We need to be a whole lot more careful because we've seen attempts to burn us and to burn our users. We will certainly see more of them. It's not going away. Tooling. Plumbers, of course, developers need good tools. And there's all kinds of tools out there. I don't think that we've always had the best tools that we could, which is kind of, it's interesting when you think that we're a bunch of hackers and we're developing code for ourselves, that we haven't always created the sort of development tools that we could make the best use of. Because in particular, I like to point out that computers can be very good at finding wide varieties of bugs, all kinds of bugs. So some examples that I've just sort of thrown together. LockDep is the locking dependency validator that's built into the kernel. Actually tracks the patterns and the order in which locks are acquired and released. And we'll find situations where inconsistent locking ordering is used. So there may be a deadlock vulnerability out there, a deadlock bug, that will only happen to you if you're running, say, in Western Australia on a Tuesday, on an odd number day, and the moon is full, and the temperature is above 25 degrees or something like that. And this burns some user sometime, and you get a report and you don't know what to do about it. With something like LockDep, that will be found, and it will raise the alarm, and it can be fixed. Ever since that went into the kernel, the reports of deadlock problems have pretty much gone away. Valgrind, of course, is a nice user space memory debugging tool. Fault injection frameworks, how well do you test your error paths? Error paths tend to be buggy. So you go along, the code finds a problem, goes into the error handling code, now you've got two problems. Right? With fault injection, you can test those and make sure that they actually work. Sparse and S-match or static analysis tools used mostly in the kernel area and so on. So we've got some tools, but we could certainly use a whole lot more of them. If you look at some of the proprietary static analysis tools that exist out there and so on, we are not up to that level. We do not have the same sort of tooling that we could have. The good news is that I think that we're getting closer to being to a point where we can have an explosion of better tools in this area because the meta tools, the building blocks are coming together. GCC, not too long ago, would not accept plugins at all. Now it has the ability to plug code into the compiler between the various passes and look at the code, make decisions, perhaps change things. But they're hard to write. Now we've got a Python plugin that allows you to write these plugins in the Python language. It's used mostly within the Python project now to do things like check reference counting and so on in C language extensions. But you can do a whole lot more with it. I think there's the potential to do some very interesting things. Melt is a similar thing for those who would rather write their plugins in Lisp. There's just no accounting for taste. So that's out there. LLVM has a rapidly developing static analysis tool as well that is gaining capabilities. There's a lot that I think we can do if we can put a little bit of energy into these tools and have the computer tell us where the bugs are instead of having our users tell us sometime further down the road when they're much harder to track down and to fix. And just to conclude with that, yes, we need good tools, but we need to use them. It's quite common to see people submitting code that perhaps hasn't even been compiled with warnings turned on, much less run through some of the more sophisticated tools that we have. We need to actually make use of these tools to get the most from them. Hardware. I have a few things to say about hardware, because hardware is a pain for software people. This is a diagram I put up occasionally. This is an embedded system. This is a little system, right? What it is a diagram of an OMAP 5430 system-on-chip processor. And if you look at it, you see that this isn't just a simple device. There are 4 ARM cores on this thing. These are actually pieces that are marked as being ARM cores. There's probably at least a couple more in there that are not actually indicated as such. There is an image signal processor, there's a video accelerator box, there's the whole audio processing system, many of which are actually complicated subsystems that break down in their own rights. All right, what we have is a very complicated device. You throw on top of that the power management structure, which on a system like this is quite sophisticated, and which overlays an entirely different topology on top of this hardware. And then the clocking management system, which may or may not match the power management system. And what you have is a piece of hardware that is non-trivial to use at anything resembling its real potential. And that leads to a whole lot of software complexity. So I put down things like asymmetric multiprocessing. I noted those 4 ARM cores. I didn't say anything about them all running Linux. In fact, there's a fairly good chance that some of them are not. They may be running some specialized DSP code that is, if nothing else, accelerating your video playback or something like that. There's a lot of things you can do with these cores. So now we're in a situation where we have multiple CPUs all running on shared memory. Right? They're all sharing the same memory, but they're running different operating systems. We have to somehow make them cooperate with each other and expose that capability to user space in a way that can actually be used and in a way that can be maintained going into the future. This is complicated. So you got memory management concerns, exposing this sort of stuff, power management. The code is getting a whole lot more complex in this area, and that will continue to do so. And I just threw out one example of a very small corner of this whole thing, which is called the media controller interface. A video acquisition device, something that, say, manages the camera on your handset, can be thought of as something that's just grabbing video frames from a sensor. But on a system on chip, like the one I put up there, it's a whole lot more complicated than that. There's the acquisition hardware. There's a little module that can do lens distortion correction. There's the rotation and cropping engine. There can be scene detection engines. There can be a face detection engine in there. There often is on some of these OMAP processors. It will go through and tell you where the faces are. All of that. And many more things like this. And there's a set of rules that allow you to route that video data through those different boxes, or not, as you see fit. The media controller interface is an attempt to export what's essentially a patch panel interface to user space, so that user space can actually configure all this hardware and use it the way it wants to do it. It does export the functionality. But as far as I can tell, there has never yet been a program written in user space that can use this interface in any kind of general way. What you see is a program that has been written that understands how this particular system on chip works, and it can configure that one specific piece of hardware. Nothing more than that. We have not yet found a way to handle this kind of complexity in a general way so that you can write a video application that can use all that functionality, and it will work on whatever hardware that you might choose to run it on. It's going to take quite a long time for us to figure out how to make these interfaces work. I think we're really just beginning with some of that stuff. Related issues, control over hardware. This has been talked about a few times recently. Life is relatively good, could get better, could get worse. But how many of you are running something like CyanogenMod on your handsets? Not too many, but there's a handful of folks who are doing that. The nice thing being that we can do that, right? We have systems that were once totally locked down. Now the software on them is mostly free, even if it's still not all as free as we would like it to be. Things have come along pretty well. So they could get better, or there are obviously attempts out there to make it worse. But I don't really want to talk about that so much, so I want to talk about something else, which is how this hardware is designed and how the products as a whole are designed, and whether we can actually get the attention of the manufacturers here. This came to my mind last August when I was at a conference in Taipei. And I saw presentations from representatives from the GNOME and KDE desktop projects, one right after the other. And they both got up there, they both brought up their tablets, and they said, our desktop environment now works on tablets. In fact, we think it's the best thing to run on tablets. And if you are a tablet manufacturer, we would really love it if you would run our desktop software on your tablets instead of something else. So I looked at this and I said, okay, this is cool. It looks like pretty nice software. But these guys are scrambling still to throw their software onto these tablets that are already out there, that have been designed and put out there to run something else. And what came to my mind is the idea that we're still chasing taillights in the dark at this point. We're still running after them saying, here's our stuff too, we could do this. But it's not designed to run that stuff to begin with. And so you can see how this expresses itself in a number of ways. If you do see a tablet running something based at least on a Linux kernel, you get something like Android. Yes, it's a nice tablet. You can do fun things with it, but it's not something that we really had a hand in designing. It's not even something we can necessarily get the code to for perhaps months at a time. If we do get the code, it's an after-the-fact sort of dump of the code. It's not something that we're really involved in creating. This is my old music player. Best music player I ever had, even though if it's the size of a pack of cigarettes and heavy and so on. This is an iRiver H340. And I used it until I couldn't replace parts anymore. I basically wore out the switches on the front and they wouldn't work anymore. And the reason it was nice was not that the hardware was nice, although the hardware was fine. The reason it was nice is because it ran Rockbox. Rockbox is a GPL licensed music player firmware. It's designed, it works just for that, and it is really nice. It makes a music player into a device that is far, far nicer than anything you will find on the shelf in your local electronics store. But if you want to get a contemporary device that runs Rockbox, you're basically out of luck. It's not there because none of the vendors will support porting the code to their devices at all. So the Rockbox developers are trying to scramble after the fact, trying to reverse engineer the hardware, figure out how to get a firmware blob to actually load on it, and all the usual stuff. So that by the time Rockbox runs on a new device, the only place you can buy the device is on auction sites and other places like that. You're buying them used because that device has long since gone out of production. This is really a shame in my mind because it wouldn't be that hard for a manufacturer to get together with the project, design a product around Rockbox from the beginning, and ship something that's way better than what they're shipping now, for a whole lot less than what they're spending to write inferior software for the devices that they are shipping. We don't have that communication there that makes this happen, and that hurts us, it hurts them. We could really be pushing things forward in this area in a way that we're not. This is a Netgear WNDR 3700 V2 router. Very nice little home router device. Quite an open device. In fact, this device comes with a version of OpenWRT on it, which is kind of a nice thing, except that they forked OpenWRT a few years ago, threw on some of their own sort of crappy front-end stuff and their own branding on it, and they're sticking with that. Right? The first thing anybody who knows what they're doing does with this is they download a real proper OpenWRT or other router firmware and they stick it on there and they run the right thing. But the OpenWRT people had to work really hard to do this. They had to get the code out of Netgear, which to its credit, Netgear is good about living up to its GPL requirements in that regard. So we have the code, even though this is running a whole lot of out-of-tree kernel stuff on it. And everybody has to scramble to produce something that could have been better out of the box at less expense to the manufacturer to begin with. It's sad to see this happening in an area which is really some of the most open and most cooperative hardware that we have anymore is these home routers. It's a nice area of hardware, but it's still, the connection isn't there. They aren't working with us. We're scrambling after them to put our stuff onto there. This is the infamous Nokia N9, which is perhaps the best attempt, or what could have been the best attempt, to actually develop the software in a relatively open way and the hardware together, and to make something really nice as a result. From what I hear, it is really nice. I've never had my hands on one, and probably never will. I think that MeeGo and all that went around it is a really sad example of a wasted opportunity. I don't know if we'll get another one like it. But it can be done. It can be done. I think that we really can try to somehow get closer to the people who are making this stuff and produce something that is more free and more useful to everybody involved. Just to summarize, Linux-based devices are great. If they're hackable, that's even better. But how can we be more involved in the conception and design in the first place? How can we take that next step and actually have a say and have a handle in the creation of this sort of hardware? And that was where I was stopping on this topic until the talk right before mine in this room, when they put up an example of a piece of hardware that is done this way. You would think I would have thought of this having actually written some of the drivers that run on this particular piece of hardware, but I can be a little slow that way. But this is the OLPC tablet, which really was designed to run free software from the outset, and it looks to be an awfully nice device for at least for a set of specific use cases. But it's really the exception and not the rule, and I wish we had a lot more of this as the rule. All right, something totally different, the concept of Linux only. We'll write our software, it only runs on the Linux system. I'm going to date myself, but once upon a time, if you were distributing software for people, it was written for a VAX. You were sending it around on a half-inch tape, and life was good because you only had to target that one architecture, and things went pretty well. Until the day came when VAXs really weren't cool anymore, and people wanted a computer that maybe only took 2 or 3 people to lift. So all the world became a Sun OS box, and all the software was written for those, but that didn't last. When we went through a phase where everything was written for 8-bit pseudo-color frame buffers, and if you tried to use your graphics hardware to its full potential, a lot of the software wouldn't run. It was really annoying for quite a few years there. We went through a phase where everything was a 32-bit little Endian CPU. It took us a long time to clean that one up too. Right, so now are we going to say that all the world is a Linux box? Right, there are people out there who are saying this at this point. At least in the free world, Linux has pretty much overshadowed anything else that is out there, and it's really the only thing that we need to be concerned with. Now, I think back, once upon a time when we were just getting started, we really depended heavily on portability. It was really annoying when software wouldn't port to Linux. And a lot of us went through a lot of that, trying to fix that sort of stuff. And are we really going to change our tune now? I think it was actually at LCA some years ago where Dave Early said that, contrary to previous practice, the DRM tree, the internal graphics tree, was no longer going to carry the code for support of the BSDs anymore. They couldn't afford it, that the BSD people weren't carrying their weight in terms of pulling this stuff forward, and that the BSD code was going to get dropped out of the DRM tree. This, of course, hurt the BSDs. They have since fallen behind in their graphics development and their graphics performance, and they don't have the sort of capabilities that we do. So one might think, okay, this is really sad, but you have to ask, would we really like to go back to the days of 3, 4, or 5 years ago or more when our graphics were terrible, when we didn't really support much hardware, and that which we did not support very well? Do we really want to go back to those days? And I think the answer is probably not. I think that we have to say that we need to go forward, and if we have to drop all this stuff, we're going to do it. So the only thing I'm really going to say here is this notion of Linux only may be inevitable, but let's not be too arrogant about it. And let's try not to forget that there are other free systems out there, and let's not do it gratuitously. One more thing that I'm going to talk about is something that I first heard characterized by Thomas Gleixner as the platform problem. This is something we see a lot of. The idea behind the platform is that you, working on a project, have a little bit of code that you control. That's your little area of code. That code interfaces to this big black box platform that is simply there, it is established, it is set in stone. You can't really do much about it. Right? This certainly was an applicable mindset in the days of writing a program for a proprietary operating system, because you really did write for a black box platform. But it's not necessarily true anymore. You see a lot of examples of this happening, though. The ARM subtree in the kernel is certainly an example of the platform problem. You've got somebody making a specific system on chip work, so they have their little area they work on. All the rest of the kernel is a black box. It's a platform, they can't change it. So if there's something in the rest of the kernel that does almost what they want, but not exactly, you copy it. You bring it over, and you tweak it, and you make your own copy, and you make it work the way you want it to work at that point. That has happened a lot in the ARM tree, and that's a big part of the subsequent mess that we are now trying to clean up. X386 was a fairly classic example of that. We've got a server, it runs in user space, so we will solve all of our problems in user space. A whole lot of problems with our graphics resulted from this idea that we have to keep this stuff in user space because that's where our project is. Once that particular platform barrier was breached and a lot of that code moved into the kernel, things started to work a whole lot better. Opportunistic suspend is Android's approach to power management. It's an interesting sort of inverted version of the platform problem. In this case, the Android developers said, well, okay, we've got control of the core platform, but we have no control over all the applications out there. And these applications, some of them are going to be written by idiots, and they will waste power and wear down the battery, and then people will say that Android has no battery life. So the way we will solve that is to not fix these applications or create a situation that causes these applications to get fixed. The way they solve the problem is to simply shut down the system hard anytime the core thinks there's nothing interesting going on. Right? That's what an Android phone does. It just puts itself to sleep if it doesn't think there's anything happening. And if there's an application that wanted to run that doesn't have the privileges to override this behavior, it just gets shut down at that time. So they fix it that way instead of trying to fix the wider ecosystem. Asynchronous I/O has been implemented several times in Linux. We've got a couple of user space implementations. We've got an in-kernel implementation. There's never been a comprehensive implementation, which is why after 20 and some years of Linux development, we still have terrible asynchronous I/O support. It's really awful and could really be done better if it were done with a different sort of approach. So there's costs to this. A lot of duplicated code, inefficient solutions, bugs, and so on. When you've got several copies of code tweaked slightly to solve problems rather than fixing things at the core, then you've spread out your developer effort. You have people fixing bugs in one place and not the other, and you're not developing really good quality code in the core the way you need it to be. So you lose a lot of opportunities that you could have with a wider view, where you can have much more comprehensive solutions to problems, right? Better abstractions, more eyes on the code because you've got less code that is serving more people, and developers who understand the whole thing a whole lot better. A couple of quick examples. Once upon a time, every wireless driver going into the kernel seemed to drag its own 802.11 layer with it. There were several of them in the kernel at that time. It is not, I think, entirely surprising that that was happening during the time when our wireless support was terrible. Right? Linux wireless support was awful for a long time. There came a point where we brought in what became known as the Mac 802.11 layer and said all drivers that need software Mac implementations will use this layer. And we ripped out all the other 802.11 layers, rebased all the drivers on this one. Now we have one core handling all of the software Mac stuff. It improves for everybody. If one driver needs this code to work better, needs a different set of functionality, they add it to the core, it's there for everybody. And now we have good wireless support. And this was an important step in doing that, was getting rid of all these silos where everybody thought they were doing their driver on an immutable platform and fixing the platform instead. There was a period of time where a lot of laptops running Linux would get something on the order of half the battery lifetime that they would get running Windows. This was embarrassing. Then one day a guy named Arjen van de Ven came along with a tool called PowerTop. PowerTop would monitor the behavior of the system and tell the user what was causing the system to wake up, whether it was in the kernel or in user space or wherever. Didn't matter. This is where the wake-ups were coming from. And people could look at it and they could say, okay, well, this driver needs some work over here, but why exactly is my Office suite waking up the system 10 times a second to do nothing? It took literally only a matter of months for people to use this tool, find the problems anywhere in the system without regard to platform boundaries, get them fixed, and to fix most of our power management problems, at least on laptop type systems. Once you looked at the system as a whole, things got a whole lot better. There's a whole lot of other examples that one can think about out there, challenges that are still there. Buffer bloat is a classic platform problem, and we've got too much buffering at all levels of the network stack, happening anywhere from applications to host systems, onto routers, and so on. Any kind of solution to this problem requires looking at the whole system and not just fixing one piece. There's only so much you can do by fixing one driver or one system this way. Marvell-Cam is just something that I found out. Years ago, I wrote a driver for, is it still? Don't know what's going on. Years ago, I wrote a driver for a Marvell camera, a video acquisition bridge, DMA bridge. It was a PCI connected device. Put it in the kernel tree, that was fine. Years later, Marvell came around and they took that same core and put it in as an IP block on an ARM processor. I was looking at this, and while I was looking at this, somebody posted a driver for yet another one of these camera acquisition devices on a different ARM core. And I noticed that what they had done is they had said, okay, yeah, the core is the same as that existing driver in the kernel. I know, I'll copy the core out of that driver, put it into a different driver, and now we'll have two of them in the kernel. So I was able to head that one off, but we see this all the time. Lots of duplicated code that goes in that way because people, rather than trying to make a core abstraction in the platform, end up redoing it themselves. So trying to implement TCP in user space because that's the part that you control and you think you can do it faster that way. There are people who do this. Control groups are an interesting example that I don't really have the time to get into. But you've got all these controllers in the kernel that are trying to operate without actually really changing the core kernel that they're operating on, trying to be minimally invasive. And this creates trouble. They don't really talk to each other. Each one is sort of stuck on top of this immutable platform. The Android kernel code is an example of this. The Android developers said, well, we can't really change the core mainline kernel. We want these other behaviors. We'll just throw all this other stuff on top of it and do it ourselves. Now, in this case, one can plausibly argue that for the constraints they had, they could not feasibly implement what they wanted in the core in a commercially useful time. It's a matter of what happens afterwards to fix up something like that. We saw a talk yesterday, I guess it was, or the day before, I'm losing track, when Bruce talked about hardware. That maybe hardware doesn't need to be a platform anymore either. That we can actually start to make more of the hardware ourselves. I've actually seen a few talks at this conference about people hacking more with the hardware. So maybe that platform is going away too. I think there's a lot that we can do. And then there was this thing I found in my mailbox this very morning. This is just kind of routine patch review going by. You don't really need to look at the details of it other than there's a developer putting in some code, and he said he actually wrote this unloading support into his driver. And he said, well, oops, this other part of the kernel doesn't support the feature that we need, so we can't do it. So we'll just do an if zero on there and comment it all out, rather than fixing the problem at its source. We see this a lot, and it costs us a lot. So just to sort of conclude with this, I'd like to say that over many years with a whole lot of work, we have built ourselves a free operating system. We have control of it at all layers, right? And there are no immutable platforms out there. There are no black boxes. We can fix things wherever we need to do it. We can look at things at all levels of it. I'd like to add that events like this one are an ideal place to solve this because we have people from all levels of the system. We're not just kernel developers. We're not just desktop environment developers. We're not just Java developers. In fact, maybe none of us are Java developers. The point being that we've got people who understand things at all levels, and we can fix things the way that they need to be. So let's do it. Let's not be stuck with this view of things that costs us so much. And at that point, I would like to wind down. And if I haven't put you all to sleep and you have some questions, I would be glad to answer them.
If people want to ask a question, could you come down to the front? It's just a little bit easier to hand out the microphone. And well, I've got one right down the front. It makes it really good. Thank you.
A lot of us don't have any connection to the hardware manufacturers. So how can the average person, besides like writing letters and complaining, how can they get manufacturers to go, hey, you know, let's work with these people?
Well, that is a hard problem, of course, getting the
Be some sort of
manufacturers to listen to us.
I mean, there's like Kickstarter projects and stuff for open hardware and that type of thing, but I think projects like Freedom Box are trying to put together a sort of a professional sort of appearance so that they can approach these companies and they're taken seriously. Maybe we could put together a group which tries to do that a bit more.
Yeah, there are a lot of efforts at a lot of levels. If you look way down at the low level, things like disk protocol standards and various hardware level standards, the kernel developers are better represented there now, and we get hardware that actually is rational to deal with sometimes. At the higher level, at the product level, it's much harder. In some cases, I think what we may have to do is to go out and make a product and show what can be done that way. And I was inspired by the little pocket oscilloscope that Bruce Perrins had, that somebody had just designed and put together and showed that you can actually make really nice looking handheld hardware with interesting functionality. Right, the tools are getting to the point that people can do an awful lot. You don't need to have this whole huge organization behind you to do a lot of things, even if making a nice smartphone is still something that you don't do in a garage. But I think that may be how we have to do a lot of it, is just show them how it's done. And
what a Kickstarter.
Sounds like you're suggesting a startup.
Hi, if we could just go back to the ARM problem for a second. It seems to me like the root of the problem is either the SOC manufacturers themselves or the companies that are trying to use the SOC, trying to get products out as fast as possible. And they obviously think that solution to that is to copy code and fix it in their part of the kernel so that they don't have to waste time trying to get it upstream or whatever. How do you think we should go about trying to deal with that issue?
that is an education issue, because it's a false economy. It works for one product. But the point is that you almost always come around to the same problems again years from now. And then you end up having to fix things up. You know, the Marvell camera controller that I talked about is one of those, right? The core of this product is the same, even if the interface hardware is totally different, right? So if you spend just a little bit of time, and it didn't take all that much time to make it into a proper core that you could then plug into from the outside, then the next time they ship a product with this, it's there and it's waiting for them, and they can do things much more quickly. If you're into consulting in the kernel, there's often a very nice business to be had in riding to the rescue of, say, embedded systems companies that have had to rev their hardware because their old hardware is no longer available. And their stuff doesn't work because none of it was mainlined and the kernel has changed completely underneath them, right? So you can either do it right or you can pay somebody a whole lot of money to do it quickly for you and to rescue you after the fact. And companies figure this out over time, at least the ones that survive do. But it's an education problem. We have to teach every one of them, it seems, sometimes about this.
It seems like TI is slowly coming around to that with the OMAP. I mean, they've really only just gotten OMAP 3 started to be used in products, and they're already starting to talk about OMAP 5. I would hope that the OMAP part of the ARM branch is going to get tidier as time goes on.
Yeah, TI is showing a fair amount of clue there, yeah. I think it's looking good for their stuff.
I'm looking for more hands, more
Anybody
questions.
else?
And there
Over
we are.
here.
I was wondering what you thought of the problem you were saying with these devices, routers in particular, not coming with a reasonable open platform. I was postulating that it's a cultural challenge. These devices are often ODM'd out of firms in Taiwan with quite a different cultural expectation to what we've got here. And that creates a big challenge to saying, we're going to take a new upstream product and put it on, particularly as the company that then puts the brand on it doesn't really have much to do with its internal design.
That is true. I mean, there's a long chain and a whole lot of people to address. But in the case of the Netgear one, at least the outer layer of the software was put there by them. It's got their branding and their stuff anyway. Right, so they've clearly, that didn't come from the OEM. right? They may have gotten a kernel from the OEM, but the other stuff, I don't think so. You know, again, it's an education thing. I mean, sometime there will be OEMs that provide more open systems that are, among other things, more capable and cheaper because they have the best software on them.
If there is no further questions, I would like everyone to put their hands together for a very fascinating talk from Jonathan Corbett. And I would like to offer you your second gold-plated glass penguin.
Oh boy, you can never have too many penguins.
You certainly can't. Thank you very much.
All right, thank you all.